Good afternoon. This is Mark Richardson with Vibrant Technology, Marketing Manager, and I thank you for joining us today. I hope everybody is doing well. You are probably cooped up in your homes, or maybe you got into an office, but I hope everybody's doing well and you're all safe. And thank you again for joining us for another in our MEscope webinar series. Today we have Dan Ambre again with Full Spectrum Diagnostics, who's going to share with us a top 10 MEscope ODS case studies. You may have thought you were only going to get 5, but we actually are going to stretch it just a little bit. We got 10 ODS case studies that Dan's going to cover today, and we are going to take a look at both the MEscope high-speed ODS videos tool, as well as traditional accelerometer-based ODS processing. So we are going to go ahead and get started, and let me hand things over to Dan. And Dan, if you were there.
Yep, I'm here.
Sounds good.
Welcome everybody. Good to have everybody here. We had a big turnout, about a little over 200 people signed up for the seminar or for the webinar. We're a little short of that right now. Hopefully some people keep pulling on in the last couple minutes.
Yeah.
Mark said we got the top 10 MEscope ODS videos. We originally started with 5, but had a lot of fun putting them together, so we added on a few just to build the excitement. The one thing I wanted to mention, and Mark touched on it just a moment ago, was this is the top 10 MEscope ODS videos, but it doesn't stop there. We're going to also look at the traditional ODS analysis. Then I think every one of these except 2 had a traditional ODS accelerometer-based analysis that was done. The reason I wanted to make this really clear is because if you buy the MEscope ODS video software package, it includes the ODS Pro software. So you're all ready to do traditional analysis as well as your video analysis. And why is that important? Well, there's a couple of videos that we're going to talk about today that are very difficult to get a good camera angle to see what you want to see. And in those cases, the traditional ODS analysis is something you can't do without to see what the true problem is. It might give you an indication, but I have a lot of piping in some places and electrical racks and things like that that get in the way of getting a real great video. But hopefully you'll like these, and we're going to start off with a little bit of the wizard processing. I don't want to dwell on this. You can go back and download the video later, and you can read what I'm talking about, but I want to get to the videos. This is just the path to get there is the wizard. The camera, Chronos color camera, we're finding that the black and white cameras do a great job too. So in fact, Mark just ordered one and he's going to get his and play with it a little bit. You can use any camera, any high-speed camera is going to work. So if you already have one, it will work with the ODS software with a high-speed video ODS. Okay. When we start using the wizard, and this is a really good example of that. This was a power plant in a very dark conditions. I had some LED lights on this thing, and this is how the original image looked. And that looks horrible as far as being able to, see every little piece of this. There are tools within the software that we can play with it a little bit. The brightness and contrast controls, so little sliders, we move those around, and I get a pretty good image in here. Okay, it's still a little dark, still a little off. I'm going to talk a little bit more about that as we go on. There is a cropping feature in the wizard #1 step. That crop, you can draw a box anywhere, and you can zoom in.
Hey Dan, I want to stop you. I'm still seeing just the first slide. I'm not sure if yours is.
No, I'm moving.
I'm still seeing top 10 MEscope ODS videos plus traditional ODS analysis. I don't know if.
Is in the sharing button, or
make sure it says now viewing Dan Ambre's screen. So.
I don't know if I pause or make. People can see a paused version of the screen. So now. showing my screen.
Still seeing.
I'm
just still seeing that first slide.
What do you see now?
There we go. There we go.
Okay.
Now I see high-speed camera features. Okay.
There's the glitch. Mark fell asleep on me. He didn't
well, I got somebody who said they're still seeing the attendees list. So,
well, I'm gonna blame it on Mark anyway.
And I did want to mention, if you do have questions, feel free to type your questions in the questions box in the GoToMeeting panel on the right-hand side of the screen, and we will go ahead and get those questions. We'll try and get all the questions answered at the tail end of the webinar. If we don't get them answered, we'll be sure to send out an email with your responses.
All right, so where we left off before we lost imaging, this is the second slide. This is the camera. This is the dark image I was talking about and the contrast controls within the wizard. So this is within step number 1. I can play with the brightness and contrast. I get a new, better looking piece of equipment, a little more definition. There's this crop feature where we can go in and draw a box and it'll zoom in, but it's not really changing the resolution. This was a total 1040 by 1280 resolution. Now this box that was cropped is 543 by 744. So we're not increasing that magnification at all. What we'd rather do is go and take another video, zoom in on it with the camera where you get the entire video dimension pixel range in that area you're interested in. And that's would be the best way to handle it. Whenever I do a piece of equipment, I try to get an axial view. I try to get the horizontal view. I try to get a 3D and I look at all the mounts because mounting foundation problems are real important. And those are some of the things you pick out fairly easily with the ODS videos. It also has a rotation feature. So this would be if I had to turn the camera for some reason to get a vertical pump. It's not the case here, horizontal pump, so I don't really need it, but that's just showing you how it changes the axis for you so you can get a good representation. There's setting the frame rates and duration. This is the frame rate of the camera. So we have ours set to 1057 frames per second. That's the max allowable. That gives us the best resolution that we can get. The other thing here is the start and end frame selection. You zero it in from the ends, any transient events. We talked about this in the signal processing webinar just recently. What I have done is I have a 1 second piece of data in my video. So I move these sliders until this total frame count gets to 1 second worth of data. We can set distance. This is some vendors out there use a laser. This is we actually draw on the drawing and put a dimension to it so it knows what the size is at the angle we're talking about. So either a horizontal or a vertical line, we put that in, tell it what that actual distance is, and we can scale the image properly. There's a point density command, and we can go very sparse or very low density, or we can really get high density of our grid points on the screen. This is set to 8208 or a little below that. Some of the video processing we're doing now, we're getting up to 25, 30,000 grid points on the screen, and you can barely see a piece of equipment because there's so many red dots on top of it. If we went to the pixel count size, it would just be it'd be a red screen. So we do process every pixel. We don't have to use every pixel to get the animation. So that's part of the speed issue that we're working with. We extract the time waveforms from every grid point or every pixel, and we get thousands of time waveforms, depending on what resolution we're looking at. And the last step is the filter points. There are a lot of background points that we want to get rid of that aren't pertinent to the analysis. And we don't really care how the background's moving. We want to get rid of those points, and it'll speed the analysis up. And there's also foreground high motion locations. So this is a histogram, and it is looking at points of occurrence versus the overall count in here. we have a lot of high frequency points out, or just a few high frequency points out here, high motion points that we want to get rid of with this slider bar. The other slider bar gets rid of the background noise. The low amplitude points over here, there's a lot more of those in the background. And the more we slide this, the more we get rid of that. So on this side, it's high amplitude, but just a few. This side, very many background points that aren't moving. So we're trying to get the best possible look at it. The idea with the ODS videos, to get a good animation, we're looking at edges. A lot of this view here, there are no points in there. There's no definition to show us the XY motion, and that's mostly interpolated. But if we have a nice edge look to all this, we get a really good animation. All right, so we're going to look at top MEscope ODS videos top 10, number 10. This is a power plant stator coolant pump, and this is the one we just talked about. This was a picture was taken in an outage with a flash camera. It looks nothing like what the actual conditions are when it's not an outage. We had a lot of artificial light here, zeroing in on this to solve some other leakage problems at the time. This is the motion that we're looking at running speed of the shaft. So it's a low light exposure. I've elongated the image, so it's kind of grainy. It's not the best quality but it's a dark condition. It's kind of gritty environment. I wanted to throw this in here, not because it's a great picture or great animation, but because when we overlay the color contour plot on it, it gives us a whole different feel. And this is showing me the same motion, but it's showing where it's all peaking out. A lot of the motion is in this electrical box, and it's wagging a little bit as the entire motor kind of goes corner to corner rocking. We originally thought it was a misalignment, which has some similar motion, or a soft foot condition where we didn't shim properly on the feet because there was some motion down here, but it turned out to be something a little bit different. We did not zoom. This is not a zoom or cropped image. This is another image that we took. So it has all the pixel value in here. Still have all the motion in the electrical box, but down here where it should be all grayed out as no motion, this corner where the motor foot's bolted down also has motion where it shouldn't be. It should look more like this, where it's all grayed over here. I'll show you a little better image of that. What you're seeing on the screen is the optical flow, and we can look at that as intensity vectors. So there aren't a lot of practical uses for it. It's interesting to look at. The intensity vectors are showing you the direction and magnitude at any given time as the image moves. And this is at the pixel level, we're doing this type of operation on it. Here I've just taken a sparse grid and we're looking at the vectors themselves. But it's an interesting look at the motion. Back up to my color contour overlay, I can see in this view that there's something going on in the base plate. And if you've seen other webinars from me, this has been in a couple of them, and we talk about the problems that probably associated with this foot. Here's our area of interest, the foot itself, and just a normal exposure view. You can see that the foot and the foundation block that's welded to this plate is all moving at the same time. There's no relative motion in here, but it's obvious that there's something going on here that isn't going on there. This is pitching the motor. There's no crack in the weld. What we probably likely have is this is a C-channel frame structure with a plate on top, and it's pumped full of grout. And it's very likely that the grout delaminated in this area and the foot is lifting up and down. And as I mentioned before, they did lots of shimming and trying to get rid of a soft foot that didn't exist. So there's a little frustration with the maintenance group. This is the pattern where there is motion, where there shouldn't be. And it fits right around where the color change is on the deck there. And here's that last look at it. So you can see that they're definitely, even from side to side of this block, there's a difference right on the outside of it. All right, we couldn't see the other side. There's a tank back here, there's a bunch of valves, there's all kinds of equipment, close corners. There's no way to get a camera in here to be able to shoot the other side of this pedestal. So we did a traditional ODS analysis. Went through with an accelerometer, and you could see the point locations where I took data, and did a pretty good job getting all the locations I wanted. This would be analogous to the camera view that we just saw. So there was some motion right here that we're picking up in the deck where it's going yellow, and 0.15 inches per second, something like that. That's about 3 times what you'd expect from a deck or a foundation or something that's supposed to be solid. Anything over 0.05 inches per second is usually a problem, or the start of a problem. This is the side of the unit that I couldn't see. So I could take vibration measurements all the way through here on the other side. There's a much bigger delamination problem on this side. Okay, we didn't detect any cracks in the welds or anything like that. It's just that the grout is coming free from the deck plate under here for some reason. Okay, so it turns out we had to do a little more investigation into that, how they wanted to fix it. All right, ODS video, top 10, number 9. This is the spare coolant pump. This is the sister unit that was on the same skid, maybe 10 feet away. Okay, spare coolant pump in tight quarters. This is one of the ones I wanted to show you because we could barely get a good angle to see what's going on. It also had a rocking motion. And so the first couple slides here are showing us that tipping motion of the motor, very similar to what we saw in the other sister unit. And that's all at turning speed of the shaft, 3,600. We put some color contour on it, and we can see some motion here in the foundation and the foot, but it doesn't look like relative motion. We're going to need a better shot of that to see what's going on. This was my best shot view at the other side. So here it was open. I could put my camera in line with it and see fairly good this foot, what's going on. But it looked like it was moving in phase with each other. This is the other side, and I can see some lifting. I can see the motor tipping here, but there's just so much equipment and electrical cables and plumbing lines in here. It's very hard to get a good shot in there. Put the color contours on. Most of the motion is up in the top of the motor as it's tipping. There's not as much down here, but that's pretty realistic to what happens in machinery when you have a loose mount. You get very little motion in the mount, but it's out of phase, and the higher motion is higher up on the structure. So you're like wagging the tail. This is the close-up of that mount. So I got on my belly and crawled in there and got a good camera angle and shot this. What I was looking for was a loose bolt where this would be lifting somehow, or any change in this line of contact here. So there's a shim under there. It looks like a crack, but it's just a long shimmed interface. If there was looseness, this would be changing, and there's virtually nothing of a change here. The block's moving underneath, the spacer block, the foot's moving with it. The bolt seems to be tight and not pulling out. So you see the end bell of the motor right here. So tight corners. This is another shot down the length. So we're behind the motor and looking at the pump. We see a lot of motion in this electrical line here and something blurred right there. When we put the color contours on, the electrical conduit is moving around quite a bit, and the edge of the motor that's rocking can be found here. That's that blurred image right there. A little out of focus. Here it just tells me there's a lot of motion. The rest of this is all scaled. So this is roughly 2.5 mils of motion. Over there, it's mostly green with a few yellow spots. So it's less than 1 mil of vibration. So pretty low, especially for 3600. This is top 10 ODS video number 8. This is a power plant spray pump analysis. The spray pump is used to knock the fly ash down. So it gets it wet and damp. It drops to the bottom of these vats that are supporting it. And every once in a while during an outage, they'll get a bobcat in there and get big dump truck piles of this stuff pulled out. So it's nasty, caustic stuff. The pump itself is just water, so it's spraying water up there to get the sludge wet and keep it out of the stack. Oh, design of the structure. It's a belt-driven fan or belt-driven pump. This platform has given them all kinds of problems. So every driving force, we have two different shaft speeds. We have pump speed, we have motor speed, we have belt frequency from the pulley system, and the multiples of all of those that are exciting natural frequencies in this frame. Not a great design. This is the motor platform at the turning speed of the motor, so 1800 RPM. And it's got a vertical bouncing motion, and we see that in the close-up image. What we're looking for is any loose interfaces. We really don't see any. We see a lot of flexure in the support structure that's holding it up, but there's highly amplified in this case. This is another mode. This is motor platform resonance near 1 times RPM of the pump. There's a twisting motion. It's a little bit of thrust, but a lot of twisting in the platform. You see the close-up image, a little slower animation, but it's just flexing the structure here. Okay, and all these little bolts, slotted bolt holes, are to adjust the belt tension. And so every one of these pumps, there were like 25 of them, and they were all a little bit different, but they all had natural frequencies in the platform that were giving them fits. This is the ODS analysis that was done along with it. So accelerometer-based, I can't remember how many locations we took, but probably about 40 locations or so with a triaxial accelerometer. And these are a couple of the modes. This is the pump rotational speed, very close to that. And it was showing that horizontal motion. This is the close to the motor speed, and it was causing a twisting and a thrust motion in the platform. So very close to what we saw in the unit 203, I think was the unit we were looking at. This is a number 7 on the list, a power plant return air fan. And it was a direct coupled fan, center hung on 2 bearing pedestals, driven by an electric motor, AC induction motor, 1800 RPM. And the data, I should have thrown the data in here, but it was a whole series of harmonics, 1 through, I think, 7 or 8 times running speed, indicating a looseness condition. And they had lots of problems with looseness. It would either come loose on this bolt, this interface. They really didn't check too much down here. They just made sure everything was tight, but they'd over tighten and they'd lose the bearing. They'd under tighten, it'd be too loose, they'd lose the bearing. And they couldn't get the combination exactly right where the bearing would run very long, but they were changing these out every outage. What's interesting here, you can see in the image, the rotation of the shaft and the thrusting of the bearing. Okay. So FFT analysis says looseness, but it doesn't say where. Okay, the image is going to tell us in a minute here. We took a close-up of the pillow block or the bearing housing. We still see the rotating shaft. We can't discern any motion up here, just the whole thing is moving. There's the split line of the housing without any gaps opening up. And down here, it's awful dirty, but there's no relative motion between the bearing plate and the bearing itself. We did find motion down at the base. So we took a shot or two on each side of the piece of equipment. Normal exposure, this was one of the first modes. This is at 1 times RPM. This is the colored contour version of that. So we do get some yellow. It is bouncing, but all the red is on this side. So the highest vibration is a little higher on the inboard side of this toward the fan, and this would be the outboard side of the fan. So vertical bouncing motion, a little bit of pitching. This is the motion that we could see at half of running speed. So a lot of times when you have looseness conditions, you can excite harmonics of running speed, multiples of running speed, but also you can excite fractions of running speed. This was the 1/2 fraction, and its direction was thrusting motion of the unit. Okay, and again, in the color contour view, we can see more motion on the inboard side than the outboard side. Now, what's that telling us? Go back to the original image, and you can see it now. And like a lot of foundation problems, the higher you go up on the structure, the more vibration you're going to get. So up here at the pillow block, you're seeing more vibration, but down here is likely the cause of all that motion. Not that any bolt is loose in itself. They checked all these and they seem to be tight. It might have pulled out of the grout a little bit, or we might have fractured that base plate grout interface, and we got a little soft spot in here behind the pillow block. We couldn't see anything, just it's a logistical nightmare, and everything's dirty, and it's hard to get a good look at if there's a crack developing, but this is the best guess of what's going on. So we're getting all this motion. It's a looseness condition. It drives a lot of motion up here, and it impacts the bearing life. We did have a traditional ODS-based, accelerometer-based analysis done. And to tell you the truth, I missed this first. I can see this bearing housing moving, and it's mostly a thrust and a little bit of twist in it. And I'm thinking, well, it's got to be some looseness in this area, but we can never find it. When you look down here, we did take measurements across each interface all the way up on every corner, and we mapped it pretty good so that we could see if any of these bolted interfaces were loose. And we see a little slight instance of out of phase motion. And it looks like as the bearing's moving in this direction, it opens up, and as it moves in the other direction, it's closing down, but the base plate isn't moving nearly as much. So there is some relative motion right there. That's where we got the dominant motion on our video. Number 6 in the top 10 is a power plant spray dry absorber analysis. A spray dry absorber is a machine that sprays a chemical into fly ash that binds with it and changes its properties. It's part of a pollution control machine in most fossil plants. I'd never heard of it before I saw this one. 3,600 RPM motor. There's a planetary gearbox in the bottom of the motor right off the shaft. And actually the motor shaft is the sun gear, and it has a planetary system, but the output shaft turns at about 11,000 RPM, and it spins and sprays as it's spinning, and you get this, well, it works. I'm not sure exactly what it's doing, but it creates a new properties in the fly ash, and makes it easy to not go out the stack at that point. Not the greatest explanation in the world, but here's the first ODS video. It's on the F unit for some reason. I had a picture of the B unit as they were installing one of these things, but there's a big cone here, and it's another cone structure as you go up, and there's ladders that you can climb down here, and it's kind of a mess down there, but the entire cone is moving. So this was a rigid body mode of the whole structure, and it's supported up here at the top, and the thing is basically cantilevered. So I have the whole thing moving like this. Originally I thought that can't be right. It looks too rigid body to be something like this, and I assumed it was, bolted down tight down here to something, to a foundation, but it's not. It's suspended. So this makes perfect sense. So this is a lower frequency. I think it's 1700, something like that, CPM. This is the opposite direction. So there's two rigid body modes that we're showing here. This one has a little whirl to it, but this is around 2300 CPM, I believe. So nothing on it's really moving. Everything's moving in one shot. The cone's kind of going with it, and that makes sense. This is 1 times RPM. So this is the little bit of whirl in this machine, and as it's spinning, and this has a lot of motion. Actually, the animation would have looked better if this box wasn't in there, because it has to rescale the response so much to see it. This box had a poor mount, electrical box, and is just swinging around. There's something else down here. One of the cables that was running down to the bottom was resonant, or moving quite a bit at this frequency. We did have a traditional ODS accelerometer-based analysis that was done. And what we found was that at 1 times RPM, we were out of phase with the gearbox. So I had to climb down that cone and take measurements down here around the top of the gearbox housing and at the bottom of the motor housing. So right about here is where the planetary gearbox is. That the sun gear was the center shaft on the motor, and the planetary box was a speed increaser up to the 10,000 RPM on the other side. This was 1 times RPM. This is the biggest problem. They had to disassemble this a couple of times before they got it right, but there was something in the build that was causing this, some dimension that they weren't getting right. The other two, the rigid body modes, are right here. One of them is just, as you would think, the whole thing wobbling, but it's all in phase. Everything's a rigid body. This one, it's centered on the center line, but if you look at the top here, it's a torsional mode. It's twisting. So I don't know if I missed this mode. It was very low amplitude. This was one of the bigger rigid body modes in there. I did take a lot of data. If you look over here, there's rings of 8 measurements, and each measurement's a triaxial. There was probably 80 times 3, 240 or so measurements collected on this for the ODS analysis. There's another interesting one. This is top 10, number 5. This is a power plant boiler feed pump analysis, and the boiler feed pump ran at 4,900 RPM. The biggest vibration on here, we're going to see in a minute, I have a spectrum, was 3,600 RPM. There's no piece of equipment in this line that runs at 3,600. However, this boiler feed pump was sitting on the turbine deck, and the turbine deck was maybe 30 feet away from the generator, or the boiler feed pump was 30 feet away from the generator that was running at 3,600. So I got a big 30-ton unit shaking the floor, and the whole deck was shaking. And again, I saw the video, I didn't believe it. I had to go back and look at a lot of things before I could make myself believe that the turbine deck was moving as much as it was, and it turns out it was. Here's the first video that I took. And you look at that and you say, no, I must have bumped the camera. There must be the camera's sitting on something that's vibrating. In fact, it was mounted to the floor, but everything's going, on the turbine deck. So normal exposure, boiler feed pump system, the motion is not the feed pump speed. It's the motion generated from the adjacent generator exciting the turbine deck. This is the boiler feed pump gearbox. It's a system. There's a turbine, boiler feed pump, a gearbox, and then a boost pump on the end. So the whole system was doing the same thing. This feed pump gearbox, everything's in phase except this line flopping around. In the color contour plot, you can see it even better. Everything's moving in phase. So it's all moving with the deck. Nothing real exciting in the gearbox to look at or problematic. This is the boost pump, which is, here's the coupling, and the gearbox is on the other side, and it's bouncing around as well. Okay, everything is in phase on this one for the most part. All the piping lines going to and from the units, and everything's moving together. So no misalignments, a lot of motion, no loose feet, anything like that. We couldn't find anything that would cause this except for the deck is moving. So we did an ODS analysis, a traditional accelerometer-based ODS. And it shows us how the foundation's moving. So here's all my measurements. Here's my original data down here, 3600. We're about 0.5 inches per second. And I mentioned earlier for a foundation, 0.05 would be a number I'd be looking for. And that's where you start to get bad. So we were quite a bit higher than that. A lot of those measurements were higher up on the structure. On the floor view over here, these measurements right on the deck, we got up to purple, green, blue. We got up to about 0.1 inches per second on the deck. So about twice as high as what you'd expect. You know, the higher up, more higher up you go, like here, I was getting 0.5 inches per second on the boiler feed pump, horizontal. But on the floor, it's a vertical pitching motion across this apparent node line right here. Okay, number 4, the vertical river effluent pump analysis. Okay, there was a series of pumps all in a row here. This was the one we were interested in. They had some leaking in the foundation, which wasn't a real big deal, but they historically have had some high vibration up here on the cantilevered end. And I think they might have known a little more about what the problem was, but really didn't tell us much when we went in there. So we're shooting everything we can. And it's a difficult analysis because standing this far away, this is maybe 50 feet away, in the poor lighting conditions, this is not poor lighting for any means. This is flash photography, so everything brightens up. Pretty dark in there, big structure, pretty far away, and you're looking at small measurements, small deflections. But anyway, this is standing right next to it and looking up. And this turned out to be, we did a few shots and they weren't coming out the way I wanted them to. This is probably the best shot for seeing the 2 modes of the pump. Usually you'll have, they call them read modes, or it's kind of like your antenna on your car. As you're driving down the road, it'll go into a certain mode shape. You have one in each direction. So there's a mode shape sideways, like this is looking. This is the electrical box, so we'll go up here. So we have one direction perpendicular to the electrical box, and another one 90 degrees away from that. Okay. Oh, excuse me, no, this is the same one. This is the color contour of that. So here's the 2 different perpendicular mode, which is horizontal, and inline mode, which is in line with the piping coming out the other side. And I'll show you a picture of what the whole system looks like in a second. 2 modes, there's a lot of twisting in them. And that was kind of a hint that something's going on that's restricting the motion somehow. It should be kind of a pure left or right, north, south, east, west type motion, but something was different. And we kind of found what that was. This is a joint. This is the back of the pump that you don't see, the discharge line going into, coupled up to the wall mounted or the facility line. So this joint, they put on some big tie rods and so forth to be able to draw the 2 sections together. It was 1/2 inch off, which machining standards, that's a ridiculous amount of offset. They brought it in by drilling a bunch of extra holes and putting threaded rod in there and tightening all these threaded rods until they pulled the 2 halves together, and then bolted these tie rods in afterwards and locked it together. What they were actually doing was they were changing the natural frequency of the pump. They were putting a big slide load or twisting load on the structure, and I believe that's why both of those animations we saw earlier were pitching a little bit. So if you just look at the box here, you can see that there's kind of a wavy motion to it. This one, the inline motion with the piping line is twisting and bouncing at the same time. I believe that the mode shape is caused by a natural frequency that's too close to the turning speed of the shaft. The turning speed is 468 RPM. And if you look at these joints, you see that there is relative motion here. That line is coming apart a little bit, just subtly. You know, you can't see it live, but in the highly amplified motion, you can pick it out. So here's the ODS analysis, the traditional accelerometer-based analysis. Took a whole bunch of measurements, probably 100 or so locations. Here's that joint, but what we're doing is we're putting a twist into this piping structure, the stand, and we're seeing a little bit of that motion in the overall cantilever mode. Another thing, and I realize this is on a log scale, I did that so that I could see some other natural frequencies in there. This is running speed. There's 2 times, 3 times, 4 times, 5, 6. But this doesn't look right. This is a wide peak. It's not a clean peak you'd expect from residual unbalance. It's probably that residual unbalance is close to a natural frequency and you're distorting it and amplifying the response. We were getting about 0.4 inches per second out here on the end, and this was 25, 30 feet of pump stand. 0.4 isn't that bad for something of this size, but it should have been a lot lower. If we didn't have to bind this up or cause all that stress in it when we pulled it together, then this peak would have been a much smaller. Okay, video number 3, steam turbine generator vibration analysis. The image, it's a little cluttered in here. This is about as far away as I could get and try to get a full view. Okay, so here's our generator inboard bearing. It's coupled to a gearbox, and the gearbox is coupled to the steam generator over here with this coupling guard. So here's this, not steam generator, but the steam turbine. In a side view, you can see a little bit better. Historically, they had some problems in the coupling area. There was thrusting, there was a lot of vibration. When they took the coupling apart, it had a lot of sludging in it, and they fixed that, but they put it all back together, and it was still having some vibration issues. This is the generator outboard bearing in the normal view and then the color contour view. And you can see a little vertical bouncing. This vibration was acceptable. We just had to check everything. The amplitude was about 0.15 inches per second, as measured right here vertically on the bearing housing. The only anomaly we could really see is this electrical line was flopping around. So there's a lot of motion there. But besides that, it didn't look too bad. It was all at 1 times RPM. It was all rigid body. So really nothing that was of great alarm. We checked the mounts. So this is the outboard end of the generator. We're looking for any liftoff here. This is a shimmed controlled surface all the way around. Everything was moving in phase. We got bolts in here. Everything's bouncing up and down. One thing we did notice as we're running, right where I was standing to take this picture is the corner of the deck. And there's an expansion joint all the way around the slab. This framework was grouted in on top of that, but the corner I was standing at, the vibration level was almost as high there as it was on the bearing housing. So a little thought in my head, there's some kind of foundation issue going on. We checked it out. So this is one of those mounts. We did all 4 of them. We couldn't find anything. Everything was moving together. There was no out of phase motion. Okay, so we couldn't find a shim improper. We couldn't find a crack in any I-beam supporting the structure, but still the floor was shaking, about 2 or 3 times higher than what it should be. This is the inboard generator bearing from the one side of it. It's rotating 1800 RPM. They had a coupling guard on here, and I wanted them to remove this coupling guard so that we could see the coupling itself and see the motion that was in that. And we were going to check alignment as it was running, but they didn't allow us to do that. So some safety reasons. Everybody's too safe. Destroys all the fun. Anyway, I joke. This color contour view shows the same deal. We have some motion. There's a thrust and a vertical motion in that bearing as well. Once you get over here to the other side, not much motion on the gearbox side of this. This is something that helps document what's going on, and there's two different views here. This is the generator outboard bearing again, and what you're seeing is two locations that were selected as far as positions on the machine to be able to see what the amplitude and what the phase measurements are. And the amplitude is shown here, X and Y, and that number is changing all the time because it's a time waveform that we're measuring. So this is an ODS time waveform animation. Over here, same thing, and you can see the phase flipping as you're moving. So again, it's a time waveform animation. One thing we didn't see in the other view that I showed earlier is this gauge was flopping around. So there's a natural frequency in that gauge mount, and it wouldn't surprise me if this thing fails quite often. Over here, this is a frequency animation. So same image, same deal. We just went from a time waveform animation to a frequency animation at 1800. And here you see the phases are locked. Okay, so I have X and Y phase at this point, X and Y phase over here. The amplitudes are locked in, and that's the kind of response you'd expect from a Fourier spectrum analysis like this versus a time waveform. This is interesting. This is an orbit feature in the software, so we can see rough directions of motion. Okay, and you can pick as many points on the structure as you want and see what the orbit is. So I did that on the outboard. I picked a point right here on the top of the housing where we took an accelerometer measurement first off, and I took it out on the end where you're cantilevered a little bit. So you'd expect a bigger motion out here in the cantilever than inboard. The direction is mostly vertical at 1800 RPM. Here is the inboard bearing, and here you have a little more vertical, but you have thrust. So a little bit of thrust motion in the shaft direction and a little vertical response. This is the same scaled motion in a point taken on the gearbox housing, and there's almost no motion over there. So that's telling me that there's no misalignment in here. Okay, if you're misaligned, then each half of the shaft is fighting each other, and you're going to see very similar motion, but 180 degrees out of phase. Didn't see that in this. So it wasn't causing that floor vibration. Another picture of the coupling side generator bearing, and its color contour response. Everything's in phase, vertical and thrusting motion. This is the gearbox. So the gearbox, you can see everything is bouncing. The generator's bouncing all over the place. There's a little less motion on the gearbox, amplitude-wise, but it's still bouncing. Everything's in phase. I didn't see anything that would indicate a looseness condition or a misalignment. What we did find is that the slab that we were standing on up above with the expansion joint around it was supported by 8 columns down below. And this is the animation ODS video of that column. You could go put your hand on it and feel the motion, and it just kind of freaks you out because all the other columns were perfectly still. So for some reason, something happened to this column, and either it was overloaded, it's slightly buckled, I really don't know. But it was moving ridiculously compared to the other 7 columns. This is a hairline crack, and I tried to show you where it was in the first video here. This hairline crack was 3/4 of the way around this square pillar. Didn't know, and I can't tell from this view if that crack's opening up. But if I put the color contours on, you can see the red all the way across that crack. So the whole thing's moving, but also the crack's doing something. Otherwise, it would be all yellow and it wouldn't change with each direction. So the main problem is there's a foundation issue. Something's happening right at the corner of the slab that was generator outboard bearing, and it was causing the whole skid to bounce. And it seems like they cleaned up all the misalignment problems they originally had, but this is probably one that's going to take a little more doing to correct that column problem. This is a small paddle fan analysis that we did. This was in my office. This is a integral shaft coupled to the motor of this paddle fan. The housing, I took the outboard part of the housing off. There's a variable frequency drive, and we set the speed at 580. I have a heavy bolt in here with a couple nuts on it for a balance weight, so I could cause some imbalance in the system. There's 6 blades. There's a cut water, and this is right at the discharge. There's a change in some of the flow goes out the discharge, some gets pulled back in and compressed. And in a pump, you get more of a pulsation. This one also had a pulsation, and maybe that would have been different if I had the outer cover back on. It wouldn't have been a problem, but very interesting response that we'll show you in a second. This is the normal exposure time domain ODS. So we can see rotation of the shaft and anything coupled with it, which is the fan. But every time it goes past the cut water, you can see the housing move. And it might be a distortion in shininess. You see a little glare there as each blade passes by. But the time waveform showed 2 pulses every time a blade went by. Just boom, 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 boom. And it showed, the blade pass frequency also, but it was really strange that it was doing that, especially for a fan. You might normally figure to see that on a pump. This is the color contour. And every time any blade passes, you get all the blades to light up, except for the 2 over here. So if you're 180 degrees away, it's not exciting those 2 blades. But if you're right on top of it, these 4 blades taking up this half of the machine are all color enhanced. So there is motion in the paddle itself. My thought is it's probably the natural frequency of the paddle, and it rings it like a bell when it goes, that little blade pass frequency pulsation right there. And it's highly damped, so it recovers quickly, but just an interesting animation. I've never seen anything like that before until the next one I'll show you. This is 1 times RPM. This is a frequency domain ODS, so you don't see the rotation of the shaft, but you do see what's happening to the whole structure. This whole box and motor system and half of your volute shell is all twisting, and it just has a nice look to it as it rocks in there. And I put a different color contour on that was a little more scaled to the motion, and gives you a nice response there. So interesting. The 1 times RPM, it's doing something, and then the blade passing is pulsating as well. Okay, this is number 1. This is really interesting, and it was hard to put my finger on what was going on. This is a fan manufacturing plant close to me. They had a prototype fan. This is a belt-driven 1800 RPM motor, and the fan is driven at 16, 18 RPM. Fan has 5 blades. Interesting, there's 4 struts on the other side. So the bearing housing is supported by these 4 struts, and it has 5 blades. So there's an unusual interaction. It's a ducted fan, so there is going to be some duct that's connected here and on the other side. But what's tricky about a ducted fan like this is the clearance of the blades. If you don't make the ductings up properly, you'll put a twist into the structure and a blade will rub, and it gets a little tricky. You want to have as tight a clearance as possible for performance, but at the same time you don't want it to rub. This is the time domain ODS animation, with and without the color contours. And looking at this, you can see there's a lot of motion right there, and that's lined up with the strut Here you see a little shadow going by. You're not really seeing a lot of motion in this strut. Down here you're seeing this whole quarter here is doing some funky stuff. Okay, now what's causing it? Well, the blade pass frequency, very likely. Oh, by the way, yes, these are, what do you call them? Screwdrivers. They stuck screwdrivers in here at some of the loose joints. This is a prototype fan, so they weren't really cared about performance. They just wanted to see how it's working and so forth. And they had a couple loose spots, so they did the quickest solution. But they're bouncing around quite a bit. When you color enhance it, the housing's moving, so there's a blade pass frequency pulsation, and you can see it every time a blade passes right there, but it's also the location of the strut. So when each blade passes, you get a pulse here. Over here, at that same moment, you're between blades. So you get a pulsation, and then you get a half pulsation on the other side. So here's the other strut through here between blades. You get that other pulsation. Strange combination. Oh, well, I got a better view. I got a little zoom in view. And you're seeing the pulsation effect on the housing, on the strut, and on the blades themselves. And I wish I had a few more videos of this. I would have really gotten in tight and watched each blade individually. Would have been interesting to see. And last of all, I believe, is this is a normal color exposure close up with the motor mount at the top of the of the duct structure. And there was two rigid body kind of translational and not orbital, but ovalization mode of the ducting. What I was really looking for was any looseness in the motor mount, in all these bolted structures that were used to slide these slide slots so that you could tighten the belts and so forth. But there was no looseness in here, just rigid body motion. But it's a nice look at it. All right, that's it. If you guys are interested, if you have any questions, I'd love to answer them for you.
Yeah, we did have a few questions here, and let me scroll down here. Some of these may have gotten answered in the duration of the presentation, but we'll go ahead and ask them anyway. Can you combine the two ODS options, video with accelerometer data? That question came in from Marius Stoyan.
Actually, no. The video is pixel motion. So you'd have 1.3 million or so pixels on the display, and all those pixels are moving. The traditional ODS is an accelerometer, so you'd have maybe 100, 200, 300, depending on the size of the machine, measurement locations, and you'd get a much sparser look at the data, but the overall motion is pretty clean. No, but you can't mix the two. You do one or the other or both. And typically I do both. I'll do a video and then I'll do an ODS animation as well.
Okay, another question here. Is there any sort of accelerometer on the base of the camera or camera support that measures input vibration into the camera? Based on what I'm seeing, I would guess this is supposed to be for qualitative analysis and not to pick out actual acceleration or deflection values. Two-part question.
You do get a spectrum and waveforms for each location or each grid point, and you can look at all the data if you want. I'll look at the image first. If I see something strange, I can look at whatever pixel locations are causing that. I can zoom into the image and see where the motion, all the true motion is and how it's located. I don't know if I answered the whole question or not, but
the second part, I would based on what I'm seeing, I would guess this is supposed to be for qualitative analysis, not to pick out actual acceleration and deflection values.
Yeah,
I think you may have answered that. So.
Yeah, I think I answered it. But what I also do is I usually take an accelerometer measurement. Like here, on this unit, this was the turbine generator. I took bearing measurements.
Oh, we're not seeing it.
Yeah, we're not seeing it. But then just to quantify, am I in the ballpark of my ODS?
Mm-hmm.
But yes, I am. I'll get that frequency. I can convert it with the signal processing parameters to velocity and peak to peak or peak, whatever you want to use as far as amplitude, and you can correlate your data.
Got a question from Dave Yantek. Do you have any experience using the video capture for transient analysis?
Actually, I was just going to do that. I have a job coming up in a week or so that I was going to do video and try to capture a modal test, a natural frequency test. So I hit the structure with a hammer, ring it like a bell, and capture that on the camera. And I should be able to see all the modes of the structure in that direction. Kind of excited about it because I haven't done it before, so it should be kind of interesting.
Okay, another question from David Ansbijian, and apologize if I'm not saying your name correctly there, David. These video captures and processing are great for stationary objects. Can we use this technology for moving structures like robotic arms or robotic assisted shelving movement? Good question.
Yeah, I think we can. This is a large scale movement that we would normally try to get rid of in the filtering, but I think it's something that can be done. It's now, instead of really judging the motion, you'd be looking at the arcs or the changes in location of a point as the image moves. Yeah, I don't see why you couldn't do it. It would be more analogous to the orbit plot that I showed you before, but then all the points would be orbits all over the structure, or at least all the joints. I don't know if that makes sense, but yeah, I believe that that can be done with video processing, and it'd be a lot easier than with accelerometer-based motion. Anything else, Mark?
We had one comment. Christopher Rode wanted to explain to you what I believe it was the slurry pump with the cone.
Yeah.
He
oh no,
he said
absorber.
Of the absorber. Okay. He says that it is used it sprays a lime slurry in the flume gas. If density gets too thick, it can cause a large imbalance and then clear out with a flush. Ours sits on a rubber donut mount, no fasteners. So just to kind of wanted to tack on, I think you were trying to explain it a little better. It looks like he's got one in place. So they keep going. Yeah,
they clog all the time. They clog, quickly. So every month or so they're changing. They have some that don't run, and they're the spares. But yeah, they're always in the shop getting cleaned out. It's a nasty process.
It must be.
I was trying. There it is.
There it is. Spray dry absorber. That's it. Yes. Great. Well, that's all the questions we have right now. And I do thank everybody for sending in your questions. If you have additional questions that you may think of after the presentation, feel free to email them to us at webinars@vibetech.com. Incidentally, this webinar is being recorded, so I'll be sending out the recording in an email probably within a few hours. It takes a little bit of time for GoToWebinar to process, but we'll go ahead and get that link. And then we'll also go ahead and publish that out to the VibeTech website. And you can also go back and review any of the webinars that you may have missed in this webinar series. There are 4 of them out there on the VibeTech website right now, so you can go review those. With that, I think we'll wrap it up. Thank you, everybody. Be safe, and I hope to see you all next time. We'll doing another one of these probably here in a couple of weeks, so keep an eye out in your emails, and we'll send out another invitation.
Yep. Thanks, everybody. Appreciate it.
Take care.